Yeah, okay. Hi, everyone. I'm Tomogno. Thanks for being here. I'm a postdoc at Rutgers in the group of peers Coleman. And today I'm going to be talking about Luttinger counts in SUN invariant Kondo models. So first, I'll talk about an exact result for the Fermi surface volume that works for arbitrary n. This is an extension of Hoshikawa's construction for SU2, following earlier work by Leaf, Schultz, Mattis, and others. Extending this theorem to arbitrary n allows us to connect to the large n limit and the resulting intuition from mean field theory. Lastly, I'll explore the implications of this result for the volume of the spin-on Fermi surface in U1 spin liquids and suggest a simpler way to think about the small Fermi surface in the FL star phase. The Kondo lattice model describes a lattice of spins immersed in a conduction sea of electrons. As a result of the Kondo coupling, the spins ionize into heavy fermions, which enter the Fermi sea, and the resulting expansion of the Fermi surface is supported by experimental observation of a jump in the magneto-oscillation frequencies as you enter the Kondo-coupled heavy Fermi liquid. So this model has long been one of the fruit fly models of our understanding of strongly correlated matter, and relatively recently it has also been in the discussion for the possibility of deconfined quantum critical point separating the heavy Fermi liquid from local moment magnetism. There are two limits in which our theoretical understanding of this model is grounded. There's a rigorous theorem for the Fermi surface volume in SU2, and there's mean field theory, which becomes exact in the limit of large n. And our goal today is to connect these two limits. The first step is to put the system on a torus and insert through one of the holes a quantum of flux that only couples to one of these n flavors of fermions. We can do this without ever breaking lattice translation. So the ground state evolves to an excited state of the new Hamiltonian with the same canonical momentum. Since this is a gauge symmetry, the new Hamiltonian is unitarily equivalent to the old one. And we can use this unitary transformation to go back to the initial gauge we started with. And in the initial gauge, if we evaluate the momentum of the final state, then this tells us what is the change in physical momentum as a result of this flux insertion. Now, in a Fermi liquid, the response to a flux insertion is straightforward. Each state in the filled Fermi sea picks up an additional momentum of A, the vector potential, and this allows us to relate the response of the momentum that we calculated earlier to the Fermi surface volume. The key step in computing the momentum response is to identify this unitary transformation that couples the unit flux quantum to just one flavor of fermions while preserving translation invariance. So I'll tell you what this transformation is, but before that, I need to set up some notation. So this is the Hamiltonian. It describes fermions with degeneracy n, say it's in a multiplet with angular momentum j, so n is 2j plus 1. These electrons hop through the lattice and they couple to the local moments. The spin of the local moments transforms according to the antisymmetric representation of SUN depicted by this Young tableau. And we've put in a Piles phase that couples to only one of the n flavors as required. So the challenge here is to find a unitary transformation that will inject this vector potential that couples to one flavor of fermions without affecting the Kondo term. And so we found such a unitary transformation that inserts the flux that works for arbitrary n. The key point is that to keep the Kondo term invariant, this gauge transformation must include a spin twist. And if we use this gauge transformation to calculate the momentum response to the flux insertion, that immediately leads to a Fermi surface volume. The Fermi surface volume counts the electron density, and for SUN, an additional term, Q over N, that accounts for the local moments. So this is an exact result that works for arbitrary N. We can, of course, do this separately for each flavor because there's a conserved U1 charge for each corresponding to each flavor. But for SUN invariant states, this is the central result I wanted to communicate to you today. I'm going to end this talk by talking about some implications of this result. But first, if you stare at this result and you recall what the right-hand side represents, you realize there's something bizarre here. Localized spins are contributing momentum. So the spin twist that we inserted imparts physical momentum to the system. We'd like to understand this better. And since this result we have holds for arbitrary n, it also holds in the large n limit, where we can explicitly see the flux insertion acting on the mean field ground state, which is exact here. We can always represent the spin of the local moments in terms of Abrikosov fermions with a local constraint on the local fermion occupation. Finite mean field results in a hybridization between the C fermions, the electrons, and the F fermions, the spinons. As a result, the emergent U1 gauge of the spinons is locked to the electromagnetic gauge, and by this mechanism, the spinons acquire charge. The hybridized fermions then occupy the large Fermi surface, and when you insert a flux, each fermion, C fermion or F fermion, gets boosted by the flux insertion. And so the Fermi surface counts all of these field states, regardless of whether they were originally electrons or fractionalized from local moments. The key point is that these spinons exist independently in the Fermi surface, whereas originally the local moment was a composite of Q fermions. Now, if you extend this picture of spin fractionalization to from large n to arbitrary n, what that buys you is a simple intuitive understanding of this bizarre momentum response. The local moment fractionalized into spinons. The unitary transformation that we discussed imparts equal momentum to both species of fermions, which is why we have an extended Fermi surface. Having explicitly seen how this flux insertion works in the large n mean field theory allows us to understand how the spin flux, which couples to the localized spins, can impart additional momentum to the system. We realize that this prescription works just as well for pure spin models. So if you'll consider a SUN invariant Heisenberg model, the spin twist imparts momentum to the Abrikosov fermions. And if we're in a ground state with no broken symmetries and the spinons occupy an incompressible Fermi sea, then in this U1 spin liquid phase, we can show that the volume of the spin-on Fermi surface is given by Q, the filling of the spinons. And for the SU2 case, this was also recently pointed out by Elseth, Horngren, and Senthil. Lastly, we'd like to touch on this very enigmatic FL star phase of the Kondo lattice models, where the Fermi surface volume is small and counts only the electrons. In the earlier literature, the FL star phase has been discussed as harboring an instance of a very interesting topologically ordered state, the fractionalized Z2 spin liquid. If you put the system on a torus and insert a flux, the flux insertion creates a vortex with momentum pi over Lx. This is called a Vizon, and this takes the system between different topological sectors in which there is or isn't a pi flux threading the torus. An alternative interpretation of FL star that we are suggesting is simply two decoupled liquids with their own independent Fermi surface. You can thread a spin flux and get the spin-on Fermi surface, or you can thread a charge flux and get the electron Fermi surface. And since the U1 of the two is decoupled, the momentum response to an electromagnetic field doesn't include the spinons. In fact, both these gauge transformations are actually respecting periodic boundary conditions. So there are no Vizons on the boundary and there's no topological order. In summary, we've made connections between the two cornerstones for understanding of the Kondo lattice models, the Fermi surface volume that is exactly known in n equals 2, and the mean field theory, which is exact in the large n limit. We've presented exact expressions of the Fermi surface volume for arbitrary n, and this connection allows us to connect to intuition from the large n mean field theory to interpret these Fermi surface volumes. We think of the Kondo effect as a fractionalization of local moments, followed by a gauge coupling of these fractionalized spinons to electrons. And a failure of this coupling this presents a simple interpretation of the enigma of FL star without invoking topological order. And in case we don't get to some of the questions, this is my email, and that's my time.
Thank you very much for your presentation. We have actually two questions in the chat. The first one is, why is the occupation for your uprecursive pseudo-fermions not necessarily 1? Isn't your spin Hilbert space changed if you allow it to be Q?
For SUN, I think for SU2 it is either 0 or 1, but in general for SUN, each spin state can be represented as 1, 2, 3 up to Q up to N fermions. So it's actually Q over N.
Okay, there's a second question. Would this fractionalization show up somehow in the dynamics of the single particle spectral function, so in principle observable in APS?
Yes. So I guess the point I'm trying to make is that yes, if you probe with APS, you can go in and probe this particular momentum, and you can calculate and you can look at the spectral function at that momentum and see that it has a sharp quasi-particle. What this tells you is that the spin-ons are independently probed. So the electromagnetic field couples to both electrons and spin-ons, and this is how we extend the notion of spin fractionalization.
Okay, thank you very much. Thank you for your presentation. We move on